Okay, hey everyone, let's go ahead and get started with lecture 25. So today we're going to be continuing our discussion of reinforcement learning. So a couple of announcements. Homework 5 is out now. I think I said I'd get that out by Monday, but I think the TA put that out on Tuesday, so sorry if you were hoping to spend your Monday night working on that. But pretty short assignment. You're just implementing and experimenting with k-means, just 2 problems, so pretty quick and easy. And it's due in 2 weeks on the last day of class, so June 9th. And again, pretty easy assignment because there's lots of other stuff going on. So tomorrow's discussion section, I mentioned this before, is going to be a project workshop. So there's no kind of planned discussion notebook we're going to be walking through. It's just going to be sort of an open office hours-like session. So do come prepared with questions about the projects, and hopefully you guys have made some solid progress on those and can use that project workshop time wisely. Since the end of the course is coming up, you all hopefully have received an email about final course evaluations. If not, the URL to do that is listed here on the slide. Please do actually fill this out. It only takes a few minutes. But this is actually quite important for me as an instructor, not only to get feedback on what you guys thought of the course, ways it can be improved, so on and so forth, but also this eval information is often used to determine if I would be able to teach a class again in the future. So please do fill this out, quite important. That's due June 12th. I'll probably send out another announcement about this, and we'll bug you guys to actually fill this out, but yeah, please do this. So just looking ahead, what the last few weeks of class are going to look like here. So today and Friday, we're going to be wrapping up our reinforcement learning portion of the course. Reinforcement learning will be on the final exam, so do pay attention this week. And then in week 10, we've got 2 lectures on advanced topics. I haven't decided yet what I'm going to do for these. I might send out a survey and see what you guys are interested in hearing about. But these advanced topics lectures are not going to be on the final exam, so don't worry about paying too close of attention, but please do still show up to lecture. And then the discussion next week is going to be a final exam review, as well as a final exam review for the final lecture of the course. Homework is due last day of the class, as I mentioned. And then the Monday after that, the project is due. So you've got about 2 weeks to wrap up your projects. And then, of course, we have a final exam on Wednesday of finals week. So lots of deadlines coming up. Finals week is always a bit of a crunch. Okay, as promised, here's some details on what the final exam is going to look like. So again, this is on Wednesday, June 14th, 1:30 to 3:30 in the lecture hall, this location. So do show up in person. It's a 2-hour-long exam, so a bit longer than the midterm, but it is going to be the same format as the midterm, so pen and pencil, no notes, closed books, no electronics are needed. So expect something quite similar to the midterm exam. I will make it a shorter exam, so you should have plenty of time to wrap it up in 2 hours. Probably be about the same length as the midterm, actually, so should be more than enough time to finish that. There again will be assigned seating. I'll just randomly assign you guys seats like we did for the midterm, and I'll announce that via Ed a couple of days before the final. If you didn't get a left-handed seat last time but want one, please do let me know. And if you have testing accommodations and did not receive those for the midterm, also let me know if you'd like those. Okay, the exam itself is a cumulative exam, so it'll cover all of the material in the course, but of course it'll be much more focused on material we covered after the midterm. But do expect at least 1 question on something from before the midterm exam. In terms of what to study, again, very similar to the midterm exam. It's all going to be sort of stepping through algorithms by hand. So make sure that you study all the lecture slides and the homeworks, know how to do all the derivations we've done in the course. And yeah, again, be able to do the algorithms sort of by hand, step by step. I highly recommend studying the midterm exam solutions. May or may not be a hint here to make sure you know how to actually solve the problems for the midterm, especially the harder ones. And I will put out a sample final exam. I'm working on that now and hope to get that out to you guys pretty soon. Okay, so things that will definitely not be on the final, so you don't need to worry about knowing the details of these. Any slides marked with these danger symbols, of course. You don't need to know the details of what's going on there. I won't be asking you questions on AdaBoost, a little bit too involved for an exam question. I won't ask you any questions on hierarchical clustering because we kind of just saw a high-level overview of that. Again, the sort of advanced topics coming in next week's lecture won't be on the exam either, and there won't be any programming, no Python, nothing of that nature on the exam. Okay, so any questions on the exam or sort of admin stuff for the next few weeks? Cool. If anything comes up, always feel free to post on the ed board. We'll get back to you as soon as possible. So today we're going to be continuing our discussion of reinforcement learning. So we'll start with a quick recap of what we've seen so far, and then we're going to build our way towards these Markov decision processes, which are again a way of sort of formalizing reinforcement learning problems in a way that we can actually put some symbols, some notation down, and actually be able to solve them. So again, reinforcement learning is all about problems where we have some kind of agent, some kind of decision maker, interacting with an environment over time. This decision maker takes actions and receives rewards from this environment, as well as observations about how the environment responds to the actions that the agent took. This agent maintains some kind of internal mental state, if you like. So the agent's state at any time step t in an iterative process is going to be denoted S sub t. And generally, this state is some function of the history of the process, where the history is everything that we've seen so far in our reinforcement learning problem. And again, typically this history is a sequence of observations, rewards, and actions. So we always receive an observation and a reward before we take some kind of action. Note that our observations might be nothing, we didn't see anything about the environment. Our rewards also might be, say, 0, we didn't receive any reward at that time step, but we always have to take some kind of action at every step. And again, the state is like the agent's mental model of what the history has been so far, and it's something you design as part of your learning algorithm. The goal of any reinforcement learning problem is to design a policy, pi, and this policy takes in the agent's current state, does some operation on that state, and returns the next action that our agent should take. So the policy is telling us what our agent should do at any particular time step based on the history. We could have deterministic policies, where the next action to take is just some function of the previous history, or we could have what are called stochastic policies, where instead of returning a single action to take, we might return a distribution over actions. So maybe our agent doesn't know exactly which action to take. It might say, okay, I think there's an 80% chance I should take this action, but a 10% chance I should take some other action. And if we want to sort of encode that uncertainty, we might use a stochastic policy. And good policies are ones that lead to larger cumulative rewards. Again, we're not interested in just receiving the highest possible reward at the next time step. We want a large reward sort of over time, over long time horizons. And of course, bad policies are ones that lead to poor rewards over time. Okay, we saw a really simple example of a reinforcement learning problem that can kind of be solved just heuristically, using some rules of thumb. And this is this multi-armed bandit problem, where we have k different slot machines, each one giving us a random reward every time we play that slot machine. And at each step, our agent chooses which of these machines to play. Our agent here needs to do two things kind of simultaneously, and it needs to balance between these two things. It needs to play machines where it doesn't know a lot about what the reward is. This is when we do exploration. We need to kind of, play around with the environment, see what actions are good to take. But of course, once we know which machines are good, or once we at least believe which machines are good, then we need to pull those arms many times, get high rewards, and this stage is called exploitation. And we saw a couple strategies for doing this, such as explore then exploit. We saw also epsilon greedy, where you kind of mix exploration and exploitation together. And we saw this decreasing epsilon strategy, which is similar to epsilon greedy, except we decrease the amount of exploration we do over time. So any questions on what we've done so far before we get into some new stuff? Okay, cool. Okay, we're going to really quickly recap Markov processes, just so it's fresh in your brain before we get into Markov reward processes. So again, a Markov process is some collection of states that we sort of transition between over time. Eventually, today's lecture, we're going to add rewards to these processes and get Markov reward processes. And then eventually we'll add actions as well to get these Markov decision processes, which again are a really handy tool for modeling reinforcement learning problems in general. So in a basic Markov process without any rewards or any actions, we just have a collection of states. And really the defining property in a Markov process is that the next state, st plus 1, given the current state, only depends on the current state. It doesn't depend on the whole history of where we've been so far. So in some sense, the current, where you are right now, is sort of sufficient to determine where you're going to go next. And we saw this example that we'll see a whole bunch more of, this student Markov chain, where the states are kind of what a student is currently doing. So maybe they're in class 1, 2, or 3. And then they can transition to other states like going to the pub, or going to Facebook, or going to sleep, or say passing a class. So we've got a bunch of different states here, and between each state, there's some probability associated with the transition. So there's a 50% chance we go from class 1 to class 2, but also a 50% chance we go from class 1 to, say, Facebook. And on the right-hand side here, this matrix P, so it's called the transition matrix of this Markov chain. And this transition matrix sort of entirely characterizes this state transition Markov chain we've shown on the left. Where again, every row here represents a starting state, and every column represents sort of a subsequent state, or the next state that we end up in. So for example, this entry here, Facebook to C1, well, there's a 10% chance I go from Facebook back to class 1. And if we know all of these transition probabilities, we kind of know everything about our Markov chain. Because again, we only need to know our current state to know what the likelihood of going to the next state is. That's that Markov property. Generally, in sort of a real-world Markov chain setup, we might know the states, but we don't really know the probabilities of transitioning between them. So to get these transition probabilities, we often need to sort of simulate this Markov chain. So we need to actually kind of run this process a bunch of times, say, start a student out in class 1 and see what happens. And using those simulations, or episodes as they're sometimes called, we can get estimates of this transition matrix by just computing, how often I go to class 2 from class 1, so on and so forth. So these are Markov chains. We saw these in the previous lecture. What we're going to do now is take these Markov chains, and we're going to introduce rewards into these processes. So this is a step of complexity above what we've seen so far for these Markov processes. So before jumping into that, I realized I use a bit of notation here that I might not have used previously in the class, and that's the notion of an expected value. So I'm assuming most of you are probably familiar with the notion of an expected value, but can't hurt to review it here. And really, whenever I say expected value, I just mean average. So if x is a discrete random variable, say like a dice roll or something like that, its expected value, I'm going to denote by this boldface e of x. And what it is it's the sum over all of the values that x can take, so that's what little x represents, times the probability that x takes that particular value. So it's just a weighted average of all the values of x, where the weights come from the probability of seeing that outcome. So for example, if I have a discrete random variable taking 3 different values, either x equals 1, x equals 2, or x equals 3, so I have 3 possible outcomes for this variable. Maybe x takes the value 1 with probability 1/4. Maybe half of the time it takes the value x equals 2, and the remaining 1/4 of the time it takes the value x equals 3. Well, the expected value then, I just plug into this formula here. I'll have 1/4 times 1 because I have probability 1/4 and a value of 1. I have 1/2 times 2 because I have a value of 2 and a probability of 1/2. And same thing for the last term. And if you go ahead and crunch these numbers, you'll get an expected value of 2. So on average, in expectation, this random variable x takes the value 2. Again, it's the average of this random variable. But we're going to use this symbol a bunch, so figured it was good to have a nice concrete example here. So let's introduce the notion of a Markov reward process now. A Markov reward process, or an MRP as I might call it, is a Markov chain that also has rewards associated with it. So formally, it's a tuple consisting of 4 different things. The first is this kind of fancy S symbol here, which is the sort of set of all possible states that our Markov chain can be in. So it's, what are the states that I'm transitioning between? P here is my state transition probabilities. So it's that matrix that I showed you guys before, telling me how likely I am to transition from state S to a new state S prime. So these 2 pieces give me a Markov chain. And now I'm going to introduce 2 new things to get a Markov reward process on top of a Markov chain. R here is going to be my reward function. So by R sub S, I mean what is the expected reward of being in state S? So when I enter some kind of state, I'm going to receive some reward from entering that state. It could be a stochastic reward, so when I enter that state, I might get some random value coming towards me. For example, in that multi-armed bandit problem, our rewards are not constants. They're random once we play those slot machines. So the reward function doesn't tell me, okay, what actual reward I received. So what's the average reward I received from being in that state? In some sense, it's, what's the average payoff of entering that particular state S? And then we're also going to introduce something called gamma, which is our discount factor. And this discount factor is just some number between 0 and 1. And we'll see what to do with this discount factor in a little bit. So altogether, these 4 things give us a Markov reward process. So let's see an example. We're going to take our student Markov chain that we had previously, and now we're just going to associate rewards with every state. So maybe if I'm in class 1, my reward is -2. Maybe it's a boring class and it's not very fun to go to. Same with class 2 and class 3, so the student maybe should change their major if they don't like all their classes. But the reward of going to the pub, say, is +1, so it's fun, so you get a reward of +1 here. Passing in your class is great, you get a reward of +10, and maybe Facebook gives you a reward of -1. It's more addicting than fun, perhaps. So each state here, we have some associated reward with entering that state. Okay, let's introduce a new notion here called a return. So by return, I'm going to use the symbol G sub t, and this is the total discounted reward that I'm going to receive from step t onwards. So maybe I run my Markov reward process for t steps. G sub t tells me, okay, how much reward am I going to get if I just continue running my Markov reward process sort of indefinitely into the future? And to compute this, what we're going to do is that we're going to get our reward from the next step. So this is the next reward I receive from my Markov process. And then I'm going to take one more step and get a new reward, rt plus 2. So this is my reward from taking 2 steps in the Markov chain. But I'm going to discount it by this factor gamma. So I take this reward, just multiply it by gamma. And if you remember, gamma is a number between 0 and 1. So it takes my future reward, and it's actually going to downweight it a little bit. And then I repeat this process over and over, but I multiply by gamma every single time. So the next sum here would be gamma squared times rt plus 3, because I'm discounting future rewards even more. And again, in reinforcement learning problems, we're often interested in very long-term rewards. So this is actually going to be an infinite sum, sort of what happens if I run my chain forever into the future. Again, it's this sum of discounted rewards. So the discount, gamma between 0 and 1, really tells me how much I value my kind of present reward more than I value future rewards. So if gamma is really close to 0, or in fact if it's equal to 0, this is kind of a myopic or nearsighted evaluation, where I care a lot more about current rewards than I do about future rewards. But larger values of gamma, closer to 1, lead to sort of far-sighted evaluations, where I really am thinking long-term about my sort of future rewards here. So gamma is a sort of factor that we can control when we're designing reinforcement learning algorithms to trade off between current rewards and future rewards. Okay, why do we discount in the first place? Why do we need this gamma at all? Well, really the main reason here is it's mathematically convenient and almost mathematically necessary. Because if we go back to this slide, well, if gamma is, say 1, if we don't have this gamma here, well, we're summing up an infinite number of rewards, and this sum on the right-hand side is going to diverge. We're going to get some infinite value for our return, and it just mathematically isn't going to work out for us. So this gamma factor, being smaller than 1, just kind of makes this sum on the right-hand side converge, so it's convenient for actually getting sort of tractable algorithms here. There are some sort of better, perhaps, reasons that you might want to discount rather than for convenience. The first is that you might have some uncertainty about your future. So perhaps you don't know sort of what to expect 100 steps down the line in your Markov chain. And so you should, of course, kind of value present rewards a little bit more than future rewards, perhaps. For example, if your reward is, say, financial, if you're playing the stock market using your reinforcement learning algorithm, Well, immediate rewards to you might be a lot more beneficial than future rewards because you could, say, invest them and even make more money based on sort of current payoffs. Okay, you could argue that sort of animal and human behavior shows preference for immediate rewards over long-term rewards. So you could argue that if you really want to build sort of a general AI agent using reinforcement learning, maybe we should mimic animal and human behavior rather than sort of really making it plan for long-term. Animal and human intelligence is really the only proof of intelligence we have so far, so we can try and copy what we know. But I will point out that it is sometimes possible to use undiscounted Markov reward processes, i.e. with no discounting factor or gamma equals 1, if you know all your sequences terminate. So that infinite sum I showed you becomes a finite sum, and you don't have any problems there. So any questions on Markov reward processes? Yeah. Right, so the black numbers on all the edges here are the transition probabilities. So if I'm in class 2, what state I end up in next is going to be random. There's an 80% chance I go to class 3, given that I'm currently in class 2. There's a 20% chance I go to sleep currently that I'm in class 2. Eventually we're going to have actions in here where rather than just randomly transitioning between the states, we're going to be able to actually take actions and decide what states we want to end up in. So eventually we'll see ways that you can kind of compute the value of being in a state, and then we can use that value to determine actions. Yeah, other questions on MRPs so far? Yeah. Yeah, exactly. So here the rewards are deterministic. So every time I go to class 2, I get a reward of -2 in my RL problem. Every time I go to class 3, I get a reward of -2. Every time I pass a class, I get a reward of +10. These could be random, but in this example, they're just deterministic. Okay, other questions? Okay, so let's now introduce the notion of a value function. So the value function, which I'm going to call v of s, is a function that takes in a state s, so we look at a particular state in our Markov reward process, and it tells us what's the long-term value of being in that state s. So what it is v of s is the expected value of the return g sub t given that I'm currently in the state s. So this is not the expected reward of being in the state. It's not what reward we receive from being in that state. It's what's the long-term value of being in that state. Because again, g is this return. It's that infinite sum that we computed before. Ideally, we want this value to be high. We want to be in states that have high values because it tells us what states we are in that are likely to lead to high long-term rewards. And our agent really should seek out these states. It should kind of figure out how to get into states that have high values in them. Okay, so let's see an example of how you can actually estimate these value functions for particular states. So we have the same Markov chain we saw before and same deterministic rewards in red. And one way of estimating the value of a particular state, which again is the long-term value, not just the single reward, is to sample returns from this process and essentially do simulation of this Markov chain. So let's say we want to estimate what's the value of a student going to their first class of the day. What we're going to do is we're going to take a student, start them out in class 1, and run this chain a whole bunch of times, and just compute that value, v of s, at every single time of sort of the simulation. So again, here I have that formula for the long-term reward, g here. Okay, so let's say I do a bunch of simulations of my Markov chain. So the first simulation is class 1, class 2, class 3, then they pass and go to sleep. Maybe another simulation is they start off in class 1, go to Facebook, class 1, class 2, and then sleep, and so on and so forth. So I'm simulating a bunch of episodes from this chain, kind of, just playing it over and over and over again. What I can do now is I can compute the value of starting out in that first state, class 1, using this formula for the long-term rewards. So I always start in the state C1, so that's my initial state. So I'll always get a reward of -2 for entering that state. So R sub 2 is -2, it's the reward I get from starting out. Then in this first chain, I end up going to class 2. Well, class 2 has a reward of -2, so here I get a -2 here, but I'm also going to discount, so that's where the 1/2 comes from. I'm discounting with a factor of 1/2. Okay, and I'm going to class 3 next. That gives me a reward of -2, just looking at my diagram up here. But I'm again discounting, but rather than discounting by 1/2, I'm going to discount by gamma squared. I discount future steps even more than the next step. So I get a 1/4 here. And then eventually I pass and get a reward of 10, but again discounting because it's in the future. So my return for this first simulation here, if I just do this computation in the first line, is going to be something like -2.25. I can repeat this by again just simulating my chain, so I get a new kind of sequence of events. The sequence events gives me a sequence of rewards, and I can compute the return of that particular sequence as well. I do this a whole bunch of times, and eventually I can sum all these up, take their average, and that's a way of estimating the value of this state, C sub 1. So it's the average return of starting in that particular state. There's a question, yeah? Yeah, so really these long-term rewards, these G's, are infinite sums, right? But in our Markov chain, we have a terminal state, actually. So this sleep state, notice there's no arrows leaving it. So I guess once you go to sleep, that's the end of the Markov chain. Try again the next day. So in this first run down here, we'll eventually reach that terminal state sleep, and there's no transitions after that. So that infinite sum just terminates. There's no transitions after that anymore. So anytime we end in sleep, our sums actually are just finite sums for these rewards. For the infinite sums, well, in practice, you can't actually, compute an infinite sum exactly unless you know the terms. So you can just take a whole bunch of terms and then cut it off at some fixed number. But again, notice that we have this decay factor gamma. It's going to exponentially decay our terms. So you only need a few of these sums before you get gamma to the 100, which is going to be something tiny, and it's going to essentially converge. But yeah, good question. Okay, so this technique is often called the Monte Carlo method, where we again simulate from our Markov processes a whole bunch and use these simulations to estimate the quantities that we're interested in. Using this Monte Carlo method, or this simulation-based method, is often really nice for large Markov reward processes. So if we have a ton of states, usually these Markov methods are quite good. But one of the downsides of this is that it often requires a lot of samples from our Markov chain in order to get accurate estimates. So we might need to do, on the order of thousands or potentially millions of simulations from these chains to actually estimate the certain value of each particular state. This also assumes that we can actually simulate our Markov reward process. Trying to go out and run this experiment, where we actually send students out to sort of simulate this Markov chain might not be something we can actually feasibly do. So we're going to see a way that we can actually compute in closed form the values for our nodes in a little bit. Okay, but let's see a couple examples of what this value function is good for, like why do we compute this in the first place? So if gamma is 0, I have a discounting factor of 0. This again means I only care about my reward at the current time step. So I don't care about my future reward at all. Well, in this case, the value for every node in my Markov chain is just equal to its reward. So I have a reward of -1 for Facebook, and the value of that node is, say, -1. So again, gamma of 0 means I don't think about the long term at all, I just want my kind of current reward. If I instead use a value of gamma, say, equals 0.9, And when I compute the the values for every node in my Markov chain, see I get quite different values here. So the value of being in this state is, say, -5. But now I start to get positive values for my nodes. So maybe the value of starting out in this class is negative, but once I go to class 2, I start to get positive values. Go to class 3, I have an even more positive value. And if I pass, well, I get a reward of, say, 10, so this is good. So what you should notice is that by counting the future, essentially caring about long-term rewards, it eventually becomes worth it for me to show up to my second and third class because these are now giving me positive rewards. Even though if I only care about my short-term reward, I'm going to get negative rewards from looking at these states. So again, the value function is a way of thinking long-term about the values of our particular nodes or our particular states. If I increase gamma to, say, 1, if I make this even larger, well, I care even more about the future rewards. And we can see here that, well, going to Facebook now becomes a very negative thing. My agent should probably avoid going into this state if it can choose which actions to take. And so we can see here that if we have an agent who can actually make decisions, well, it's going to want to seek out these high-value states because they're the ones that give us high long-term rewards. So a couple of questions. Do you have a question here? Yeah, you're right. So when we're doing this Monte Carlo estimate, we are just estimating the value of whatever particular node that we start in. So every node has a different value, right? And in this example, I'm only computing the value for this class 1 node. So I start all of my simulations in class 1. Ignore this bottom line, shouldn't be there. I start all of my simulations from class 1. If I want to estimate the value of the node class 3, well, I would need to start all my simulations at class 3. It's what's the estimated long-term reward of starting or being in that particular state. So again, this example is just for estimating the value of the class 1 node. Yeah. Yeah, another question. Yep. Exactly. So each simulation, each run gives me some value for the long-term reward. So I get a value for G for every simulation. And if I average them up over very many runs, well, I'm going to get an estimate of the expected long-term reward. So it's a sample average trying to compute this value. Yeah. As many as you can basically afford to compute. So on the order of like thousands or perhaps millions. So these can be quite expensive to actually run, yeah. Okay, so as I mentioned, this Monte Carlo method, this kind of sample-based method for estimating values of states, can be really, really expensive. So what we're going to do instead is derive something called the Bellman equations. So it's a little bit of an involved derivation, so we'll go slowly through the next few slides. So here I've got everything kind of relevant on the slide together, just to recap what we've done so far. So the value of a particular state is V of S. This is the expected long-term reward of being in that state. Okay, and these values are actually unknown to us. We don't know the value of being in a particular state. Even if we know the reward of being in a particular state, we need to somehow compute this expected value, compute this average. This is not something that's trivial to get. As we saw, we might have to simulate things. Again, this reward is the total discounted reward. So again, this infinite sum of future rewards that we need to sum with this discounting factor. But what we're going to see in a second is that the value function, v of x, can actually be decomposed into two parts. The first part being the immediate reward, so what reward do I get from entering that state, S, plus the discounted value of the successor states. So if I'm currently in a particular state and receive some reward, I can actually compute the value of being in that state by looking at what's the value of all of the potential states I could go to next. And in this way, we're going to get a recursive relationship that we can then actually go ahead and compute. Okay, and this is what's called the Bellman equation. So very famous in reinforcement learning. It's kind of the cornerstone that powers all RL algorithms. And it's something that you might actually know from like dynamic programming if you guys are familiar with that. So again, the value of a state is the expected long-term reward of being in that state. So this first line is just the definition of the value as we've seen it so far. And this next line, what I'm going to do is I'm going to take g of t and just write out its definition. So g of t is what reward I receive from entering that state, plus the discounted reward of the next state after that, plus even further discounted reward of the third state, and so on and so forth. But what you should notice is I can leave my first reward on the outside, but now I can factor a gamma out of this remaining infinite sum. So I factor out that gamma, and I get a term here that's a reward, and then plus just a single discount times the next reward. Well, if you look at this closely, this term in the parentheses here is actually just g of t plus 1. This is the long-term reward after t plus 1 steps, given that I'm currently in this state. So I've essentially taken my reward function and now decomposed it into an expected reward plus a long-term reward discounted by gamma. Well, essentially, this g of t plus 1 is just the value of what's the next state that I can enter from my current state S. And so in this way, we've actually gotten a recursive relationship where the value in my current state is the expected reward of that current state that we're entering, plus the discounted value of all the potentially neighbor states I can enter. So we'll see an example of this in just a second. But using this Bellman equation, if we know the rewards in our Markov process, and we know the transition probabilities, we can actually in closed form solve for the values of all of our states, which is something that I think is, kind of magical that we can actually, closed form get these. Okay, so let's take a closer look at this Bellman equation that I wrote out. I'm going to draw something called a backup diagram here. So let's say that I'm starting out in some particular state S, which I'm going to draw as this node at the top of my tree. So this is the state that I'm currently in. And maybe there's two states that I can transition to. I've got a state down here to the left, or I can transition to a different state down here on the right. I receive some reward from entering this new state S prime, and I'll receive some other reward from entering this other state. But each of these states, again represented by a node, itself has some kind of unknown value associated with it. But what the Bellman equation says is that the value of this state at the root of my tree is the reward of being in that state. It's, again, this term here is the reward of just being in my starting state, plus gamma times the value of my successor states. So it's gamma times, here I have an expectation, so I need to take the average value of all my successor states. And that's this term here, which, if you remember the slide I had on expected values, that's exactly this formula that I have down here. It's what's the probability of entering each successor state S prime times the value of that successor state S prime. So if I know the value of all of my successor states, of all the states I can transition to, so if I know this value and this value, well, I can compute the value up here by just plugging it into this formula down below. So again, I get a really nice recursive relationship relating the values of my nodes to one another if I know the rewards and if I know these transition probabilities. So let's see a really concrete example in our student Markov reward process. Let's say, just for the sake of illustration, that I know this node down here has a value of 0.8, and this node on the right here has a value of 10. So I know the values of these two guys. If I want to compute the value for this node, highlighted in red, let's say it's unknown, well, its value is going to be its reward, which is -2, plus just a sum of the transition probabilities times the value of each of the possible successor states. So this guy down here has a value of 0.8, and there's a probability of transitioning to this node of 0.4, so that's where this term comes in. And here this guy has a value of 10 and a transition probability of 0.6, and that's where this term comes in. So again, the value of my current node is what reward I receive, plus on average, what's the value of all the nodes I can transition to. So drawing it in this kind of backup diagram fashion, disregard the poor drawing on the right here, we can kind of compute these in a diagrammatic fashion. Okay, but to actually do this, I need to know the rewards of my successor states, and I need to know the values of those successor states. But the problem is, in our Markov chain, we don't know the values of any of our states to start out with. So what we can do is now write things in terms of a matrix equation. So this is one of these deals where you don't need to know the details, but it's good to see how you actually do this. But the Bellman equation, as we saw it before, is just the value for a particular state, a particular node. But we can concisely write this as sort of a matrix vector notation here. So V is going to be a column vector telling me the value of each possible state in my Markov chain. So if I have n states, I've got n entries in this column vector. And by the Bellman equation that we derived before, these values are going to be equal to the rewards I receive in each of these states. So I have an average reward for entering each of these states, plus gamma, my discounting factor, times my transition probability matrix from my Markov chain, times, again, the values of each of my particular states. So again, this is just the Bellman equation that we saw before, but now we're writing it in terms of a matrix vector product. And here our goal, again, is we don't know the values of these states, so we somehow need to solve for this vector V. And using a little matrix algebra, we can do that. So that's only a couple of lines here. But what we can do is we can essentially move all of our V's to the left-hand side of this equation. So I took gamma times PV, moved it to the left-hand side over here. And now I have my V's isolated, so I want to try and solve for these V's. And if I just take the matrix inverse of this guy, well, then I have solved for my values V. So in doing so, I get a closed form solution, actually, just through a little bit of matrix algebra, for the values of each one of my nodes in my Markov reward process. So this Bellman equation is super useful because it lets us compute these values, actually. The problem with doing this, though, is that it's very computationally expensive. So here we need to compute a matrix inverse, and this matrix is an n by n matrix. And computing matrix inverses is actually cubic in the number of entries. So it's going to be a O of n cubed operation, where n is the number of states, in order to actually compute these values. So if you have a very large Markov reward process, in fact, it doesn't even need to be that large, this matrix inversion is going to be totally intractable. You won't be able to compute it. And so doing this direct solution is only really tractable for very small Markov reward processes. And in practice, oftentimes we don't actually do this. It's just infeasible. In the next lecture, when we wrap up reinforcement learning, we're going to see techniques for actually trying to compute the values of these. And then we'll, of course, see what to do once we have these values. So we saw one example of how you could estimate these using Monte Carlo evaluation, again, simulating from our Markov chains. But there are other techniques like dynamic programming or temporal difference learning, things like Q-learning that we're going to see in the next lecture. Okay, so that wraps up Markov reward processes. Any questions on those? Yeah. It is a trade-off, certainly. So it depends on how many simulations you want to run of your Markov chain. If you have a very, very large Markov reward process here, like imagine you're trying to train a reinforcement learning agent to play Minecraft, right? Here, it's cubic in the number of states that you have, right? Well, the number of states you have in a video game might be essentially infinite, right? There's no way we could explore all of the possible states of something like Minecraft. So using a Markov chain simulation, well, you can at least do that. It might take lots and lots of simulations, but it's something that you can at least feasibly do. So yeah, again, this scales poorly with the number of states, whereas the Markov chain is going to just essentially it'll be tractable, it'll just take more computation. Yeah. Yeah. Yeah, in some sense you're trying to solve for these values, but you're not trying to compute sort of the stationary distribution necessarily, right? You're not comparing sort of like what states you're ending up in. You're looking at the values here. But I mean, that's potentially one way of actually trying to estimate this inverse, yeah. Okay, other questions on MRPs? Yeah. Yeah, so down here you mean? So, yeah, so what I'm doing here is that, so remember the value of a state is the expected value of G, right? Here I have an expected value of G. So I'm kind of pulling this expectation to the inside here. I'm being a little bit sneaky. So I took the expected value of GT plus 1, and that's exactly the definition of the value of that state. Okay, so in the next lecture, we're going to add another layer of complexity on top of Markov reward processes, because they weren't complex enough, where our agents can actually take actions. So once we let our agents take actions, we're going to get Markov decision processes, and really this is where sort of the real reinforcement learning action all takes place. So go ahead and wrap up for today. So again, we saw Markov processes, we saw a recap of these, which describe the evolution of our states over time, and are characterized by these transition matrices. So for every possible pair of states in our Markov chain, we have some probability of transitioning between them. We introduce rewards now to get a Markov reward process, where every one of our states in our Markov chain has some associated reward with entering that state. We don't care so much about what the reward of entering a particular state is, but rather we care about the value function of a state, where the value function of a state really tells us what's the long-term average future reward of entering that particular state. Again, we care about these long-term rewards much more than just a single sort of payoff. And we saw how we can actually estimate or compute these value functions, either using Monte Carlo simulations or for very small MRPs via these Bellman equations. Okay, and that's all for today, guys.